Now this is one of those sections where there's not actually a whole lot of notes. Most of what you're going to be learning is through doing the examples, but I'll at least derive what we're going to have for you. I'm going to derive it for you for a particle. There's another section that just basically proves that this works for a system of particles as well, but we've done that so many times now that it just seems not that exciting, so I'm going to kind of skip over it. F equals ma. Good to go? Yes. Alright, awesome. F equals m dv dt. Nothing scary? F dt equals m dv. Stop me if you're scared. Well, you can't. I'll keep going no matter what. Whenever we have d's, we always have to integrate it to get rid of the ddt's. dt is going to start from some t1 to some t2. The v vector, that's a vector, is going to start from some initial position or some initial velocity vector to some final velocity vector. The integral of the sum is the same thing as the sum of the integrals, right? If I integrate 3 plus t dt, that's the same thing as integrating 3 dt plus the integral of t dt, right? So the integral of the sum is the same thing as the sum of the integrals. That's just a fancy way of doing this. It means I can pull this summation sign out. Equals m is constant, and then if I just integrate dv, you know, that's just like integrating dx, it's x, right? So it's going to be v evaluated from v2 to v1. So I've got that the summation of the integrals of all the forces with respect to time is equal to mass v2 minus mv1. And this should start to look somewhat familiar from Physics 1, maybe. What is mv? Remember what mv was from Physics 1? mv is momentum. That's right. I mean, as if you couldn't guess from the title, since it's the principle of linear impulse and momentum. This is momentum. You probably saw this somewhere. I think in physics we use P equals mv or something like that. Well, it's not P anymore, but that's what we learned it as in physics. Momentum. So this is momentum at position 1. And this is momentum at position 2. Now what this is called in here is your linear impulse. So the idea is if you got a little particle, it's like going whee, like this, some velocity. And then it gets hit by a force, yarg, angry force. Then it's going to go a different direction. That way. I know, not rocket science. But don't worry, we'll make the problems hard to compensate for the simplicity of the concepts. How's that? Basically, you know, you've got a particle going one way, it gets hit by something, it goes another way. That is the principle of linear impulse and momentum. Not super, super crazy. Just, you'll need this later. You're not going to see it again in this chapter, I don't think, but the momentum we use is L, and the linear impulse we call I. Okay, and they're both vectors. Another way to think about the linear impulse is the effect of a force during the time the force acts. So you've got a force doing something during a specific period of time. The longer I hit something, the longer I push on something, the more impulse I apply to it. And then momentum is just directly dependent upon its initial velocity. And really the whole other section dedicated to this is just proving this doesn't just work for point particles, but works for a rigid body as well. So So there, it's done. So we'll say this works for particles and rigid bodies. Or a system of particles, so if you've got a whole bunch of things, that are all moving this way at some velocity, and then they get, hit by something, you can apply this exact same, that's a terrible picture, you can apply this exact same theory to that as well. So it applies to a particle and rigid bodies, system of particles, however you want to think about it.